Welcome back to the Deep Dive, where we take your stack of sources, rip apart the history, and then try to put that whole intellectual picture back together for you.
Today, we're tackling a question that is just fundamental. It's maybe the single greatest question in astronomy that is both right on our cosmic doorstep and, well, mind-bogglingly complex.
Which is, how did our solar system even get here? I mean, how did the sun, all the gas, all the dust and gravity just assemble themselves into this surprisingly stable, arrangement of planets going around a single star?
Exactly. And we're not just giving you a laundry list of theories.
No, this is a deep dive into what was really a 2-century-long intellectual war.
Yeah.
I mean, a battle fought by some serious scientific giants. You have philosophers like Kant, mathematicians like Laplace, all trying to explain our cosmic home.
So our mission today is to trace that history, but we're focusing on the crucial, often brutal scientific stumbling blocks, the things that kept forcing the world's smartest people to just throw out everything they thought they knew and start over.
And it all starts with this strange paradox, which, honestly, it still feels a little weird to say out loud.
It sounds completely counterintuitive, but for decades, and I mean for a long, long time, we understood the evolution of distant stars much, much better than we understood the evolution of our own planetary system.
Okay, stop there, because that's baffling. How can we possibly know more about a star millions of light years away, I mean, a tiny speck of light, than we know about Jupiter? Jupiter's right there. Astronomically speaking, it's our next-door neighbor.
Well, it really comes down to the volume of evidence. When astronomers study the life cycles of stars, they're not just looking at one, they're observing an enormous quantity of them, and crucially, they're seeing them at every conceivable stage of their evolution.
Right. We look at things like star clusters, which are these perfect cosmic laboratories. All the stars in a cluster, they formed at roughly the same time from the same initial cloud of stuff.
Exactly. But because they all have different masses, they evolve at wildly different rates.
So you get to see the whole movie, just with different actors playing each scene simultaneously.
That's a perfect way to put it. By analyzing that massive empirical database, charting countless star clusters on Hertzsprung-Russell diagrams, they could piece together how the pace of stellar evolution depends on those initial conditions, namely mass. We have a complete life cycle model because we can see millions of examples of stellar birth, adolescence, maturity, and, well, death.
It gives us a complete timeline from start to finish.
Precisely. And without that extensive empirical material, you have to realize stellar evolution would still be pure speculation, just guesswork, like it was before the mid-20th century.
Okay, so that brings us back to our solar system. Why was our situation so different?
Because when it comes to the formation of our planetary system, we were in a unique and a far more constrained position.
Because we couldn't, at least for most of this intellectual history we're talking about, we couldn't just look out and see other solar systems in different phases of their existence.
We completely lacked that real-world picture of how planetary systems look at various evolutionary stages, or even just how drastically different they might be from one another. So for centuries, researchers had to grapple with the fact that we are observing our solar system, as they often put it, in a single specimen.
Wow. A single specimen. That contains all the data about the finished product. The mass ratios, the speeds, the distances, but it gives you absolutely no direct timeline. There's no time-lapse video of the construction process.
None. It's like finding a perfectly constructed house and having to figure out if it was built from the roof down or the foundation up, and all you have to go on are the materials you see in the final bit of it.
And that constraint, that single specimen problem, is what led to 2 centuries of brilliant speculation and, as we're going to see, some absolutely crushing mathematical failures.
A long history of inquiry, for sure. It involves figures from the 18th century philosopher Immanuel Kant to the 19th century mathematician Pierre-Simon Laplace, all the way up to the 20th century Soviet scientist Otto Ilyevich Schmidt. It's quite a lineup.
A huge scope. But the sources are clear that despite this difficulty, this wasn't just stumbling around in the dark. The process of elimination, driven by hard, cold physics, was actually highly effective.
That really is the good news here. Although we still haven't solved the problem completely, the circle of possible hypotheses about the origin of the solar system has narrowed significantly.
And we're going to see exactly how that narrowing happened. It was elimination by one of the most unforgiving concepts in science, the conservation of angular momentum.
That's the dragon that slayed all the early theories.
All right, let's start at the beginning then. The foundational idea that really dominated scientific thought for over 100 years.
Let's do it. We'll start with the classical foundation, the Kant-Laplace hypothesis. This is really the origin story of the origin story. It's where the idea that the solar system arose from the lawful development of a nebula first took root. It was this beautiful, orderly, almost philosophical approach to cosmology.
And that concept established a paradigm, right? The solar system isn't just some arbitrary collection of cosmic debris. It's the result of an evolutionary, not an instantaneous process from some kind of primordial cloud.
Exactly. But here's the first critical detail. While the core idea of a gradual nebulous origin was shared, the specific visions laid out by Immanuel Kant and Pierre-Simon Laplace, who were working completely independently, were, well, they were drastically different.
Different in their starting conditions and the whole sequence of events.
Completely.
Okay, let's define those sharp contrasts, because they reflect entirely different physical assumptions. Let's start with Kant. What was his vision?
Kant's original model, this is back in 1755, was based on the evolutionary development from a cold, dusty nebula. He pictured this vast static cloud where, random gravity and particle collisions very slowly cause things to start clumping together.
So a cold accretion model. What was the sequence of events in Kant's cold system? How did it unfold?
In Kant's sequence, the denser material in the very center of the cloud started pulling in more and more stuff. This led the massive central body, the future sun, to form first.
Okay, that seems intuitive.
Right, and then the planets condensed out of the remaining, slower-moving material that was left orbiting this newly formed central star.
So, cold, dust first, sun first, planets second. That makes a lot of sense. The biggest thing forms at the center, and then it just sucks everything else in or around it.
It's very logical. But now you have Laplace working decades later, and he saw the starting line completely differently.
The absolute opposite, I understand.
Absolutely. Laplace, the great French mathematician, proposed a system starting from the other extreme, a very hot, rapidly rotating gaseous nebula. His nebula was already a vast, hot, spinning gas cloud from the get-go.
So why the assumption of hot and specifically rapid rotation?
Well, the heat was a prevailing theme in early cosmology, given the sun's eventual fiery nature. But the rapid rotation was the central mechanism for Laplace. He realized that as this huge cloud contracted under its own gravity, a fundamental law of physics would require it to spin faster and faster.
The conservation of angular momentum. This is the classic ice skater analogy, right? When a skater pulls their arms in, they spin much, much faster.
Precisely. And this increasing spin, according to Laplace, led to massive centrifugal forces, especially along the equatorial belt of this contracting nebula. He proposed that once the outward centrifugal force overcame the inward pull of gravity at the equator, rings of material would just separate sequentially.
Like dough flying off a giant cosmic pizza being tossed in the air.
That's a great image. And these separated rings, now orbiting on their own, would subsequently condense to form the planets that we see today.
And this leads to a really crucial implication for the timeline.
A critical one. According to Laplace, the planets formed before the central star was finished. The sun was actually the residue, the core mass that finally collapsed into a star after all these peripheral rings have been shed.
So, to sum it up, Kant says sun first, Laplace says rings and planets first. But despite all these contrasts, hot versus cold, gas versus dust, sun first versus sun last, they both share that same core belief.
That the solar system arose from an ordered, internal, lawful development of a single nebula.
And it was a beautiful theory. I mean, it explains so much. Why all the planets orbit in basically the same plane, why they all go in the same direction. It was consistent, it was elegant, and it just dominated scientific thought for a century.
It did. Until it was forced to collide with reality in the form of a very specific, very stubborn physical measurement.
And that collision brings us to the single most important scientific concept of this entire deep dive. This is the critical crisis, the angular momentum problem.
This crisis became clear around the middle of the 19th century. Researchers started applying really rigorous mathematics to that final, finished specimen of our solar system, and they discovered what the sources call a fundamental difficulty, a deeply counterintuitive anomaly in the distribution of rotational stock within the system.
Okay, before we even get to the numbers, let's make sure we clearly define angular momentum, because as you said, this is the concept that killed the classical theories.
It's the central villain of the story, for sure. Think of it as the total reserve of spin in the system. It's a conserved quantity in any isolated system, like the sun and its planets are, more or less. That total rotation is the sum of two main components: the axial spin of everybody, so the sun spinning on its axis, Earth spinning on its axis, and the orbital motion of the planets going around the center of mass.
And to calculate that orbital part, the math involves three critical factors. It's not just
Wow.
speed, is it?
No, and this is the crucial point. The orbital moment is calculated as mass times velocity times the distance from the center of rotation.
The distance.
Yes, which is essentially the sun's center. This third factor, the radius of the orbit, is what makes the distant planets so incredibly powerful in this whole equation.
Okay, so researchers took the solar system as a whole. They calculated this total rotational stock, and this is where the beautiful Kant-Laplace model just completely fell apart.
It defied all logical expectations. I mean, look at the mass ratio first. The total mass of all the planets combined is tiny. It's only about 1/700th of the sun's mass.
1/700th. So if you had no other information, you would logically absolutely assume that the overwhelming bulk of the rotational energy must be in the overwhelmingly massive sun.
It seems like a mathematical certainty. It's the only thing that makes sense. But the solar system, well, it decided to completely ignore logic.
What did the calculation actually show?
The START calculations show that 98% of the entire solar system's angular momentum is contained in the orbital movement of the planets.
98%. Wait, only 2% is left in the sun's own rotation.
A minuscule 2%.
But if the sun is 700 times more massive, how could the tiny planets possibly account for 98% of the spin? That feels like saying a feather, just by floating in a circle, has more kinetic energy than a charging bull. It doesn't make intuitive sense.
And that is precisely the shockwave that hit 19th century cosmology. It's all because the sun spins so incredibly slowly. I mean, the contrast is just dramatic. The sun's equatorial rotation speed is only about 2 kilometers per second.
Only 2. How does that compare to us?
It is 15 times slower than the Earth's speed orbiting the sun.
15 times. Wow. Okay, so even though the planets are tiny compared to the sun, their huge distance from the center, that radius variable in the momentum calculation, and their relatively high orbital speed gives them almost the entire rotational stock of the whole system.
And it's not even spread out evenly among the planets. The sources are very, very clear on this. The lion's share is overwhelmingly concentrated in the orbital motion of the gas giants, specifically Jupiter and Saturn.
Jupiter is the real momentum hog. It's the engine of the entire system's spin. Let's talk about the raw numbers just so we can really grasp the scale here.
Okay, we can compare the figures in CGS units, which is just a standard system centimeter gram second used for these kinds of physics comparisons. Jupiter's orbital moment is calculated to be about 190 times 10 to the 48 CGS units.
Okay, 190 times 10 to the 48th.
Yeah.
And the sun.
The entire massive rotating sun, by comparison, only holds 6 times 10 to the 48 CGS units.
Let me make sure I heard that correctly. Jupiter's orbital moment, just by itself, is over 30 times the rotational moment of the massive sun.
It is colossal, absolutely colossal. And if we then look at the inner rocky planets, Mercury, Venus, Earth, and Mars, their combined total moment is 380 times less than Jupiter's alone.
So it's all Jupiter and Saturn. They are the masters of the angular momentum budget in our solar system.
They absolutely are.
So this distribution, this physical reality, is what proved fatal for that beautiful, orderly Laplace hypothesis. Let's connect the dots. Why?
The contradiction is just. It's logical, and it's insurmountable. Think back to the nebulous stage that Laplace envisioned. When a ring of material separated from the protosun, the material in that ring, and the material left behind in the protosun, they had to have roughly the same angular velocity per unit of mass. They were, physically connected right up until that moment.
Okay, so if the velocities were the same per unit mass, then the total amount of momentum should just be directly proportional to the total mass.
Yeah.
More mass, more momentum. Simple as that.
Exactly. So since the mass of any separated ring was absolutely tiny compared to the mass of the remaining protosun, remember, all the planets are only 1/1700th of the sun's mass in total. The ring's total angular momentum should have been a negligible fraction of the protosun's momentum. Maybe 1%, maybe less.
But the observational data, the reality of our system, show the exact opposite. The planets that formed from those rings ended up with 98% momentum.
And this is the fatal flaw. The logical necessity of the Laplace model was violently contradicted by the physical reality of the solar system. The contracting nebula model lacked any mechanism to efficiently transfer such a massive amount of momentum, 98% of the system's rotational stock, from the dense central protosun out to those tiny distant outer rings.
So they needed some kind of physical process that was powerful enough to basically strip almost all the spin from the massive central star and then just fling it outward to the edge of the system.
And the internal, lawful, gentle evolution of a simple contracting cloud just couldn't provide it.
It was an insurmountable physical impossibility.
And it completely destroyed the classical Kant-Laplace hypothesis. The orderly evolution model was dead, which of course led to a really radical intellectual pivot.
Right. If internal orderly evolution failed, the natural response was to look outside the system for an explanation. The next major effort was the catastrophic alternative, the genes hypothesis.
And this represents a complete radical shift, not just in physics, but in philosophy. Where Kant and Laplace saw an orderly, almost necessary process of formation, the genes hypothesis, developed by Sir James Jeans in the early 20th century, depicted planet formation as a rare, accidental, and utterly exceptional event, a cosmic fluke.
And a fluke immediately changes the whole outlook. If Jeans was right, then planetary systems like ours should be almost non-existent in the galaxy.
Precisely.
So what was the specific mechanism for this cosmic accident?
Jeans proposed that the planets originated from material that was ejected from an already old, mature sun. So this wasn't material left over from the sun's birth. This was stuff that was physically ripped off its surface.
And the cause was external interference, a near collision or a very close passage of another star. So we're talking about a stellar drive-by, where a massive gravitational field just briefly interacts with our sun.
That's it. As that second star passed extremely close, and we're talking maybe within a few stellar radii, so incredibly close, its gravitational influence would have generated immense tidal forces on the sun. These forces would have pulled a hot gas filament, which he described as being shaped sort of like a cigar, right off the sun's surface layers.
And the idea was that the gravity and motion of this passing star would also impart the necessary angular momentum to that filament. That would solve the problem.
That was the hope. The thinking was that this filament of superheated gas would remain captured by the sun's gravity even after the intruder star had moved on, and this material, because it was pulled by an external object, would have enough initial momentum to explain the distant orbits of the outer planets. Then the filament would just cool and condense into planets.
It sounds like a plausible fix for the momentum problem, but the Jeans hypothesis immediately ran into two massive, devastating challenges. The first being the problem of probability.
Yes, the probabilistic argument against Jeans was just. It was devastating, because it showed our very existence would be an almost impossible miracle. Star collisions, or even extremely close passages, are astronomically rare events in the galaxy. Space is just so vast, and stars are such tiny targets within it.
How rare are we talking? The outline gives a calculation, a probability of 10 to the minus 15. What does that actually mean?
Well, just think about the sheer scale. Our sun is moving relative to its neighbors, but the distance between stars is immense. To figure out the probability of a close passage, say, within 3 stellar radii, you have to compare the tiny size of that target area to the total volume of space the stars are sweeping through over billions of years.
It's like trying to get two specific grains of sand on a vast beach to bump into each other, right?
It's even more extreme than that. When they did the math, researchers like Jeans arrived at that probability of about 10 to the minus 15. That is 1 chance in a quadrillion.
1 in a quadrillion. For a single star, over a single period of time. That's an incomprehensibly low number.
And it translates to the lifespan of the sun like this. Over the sun's entire estimated 5 billion year lifespan, the math suggested it had only 1 chance in tens of billions of having such a close planet-forming encounter with any other star.
And if you take that number and extrapolate it across the entire history and size of our galaxy, with its, 150 billion stars? The philosophical implication is just profound.
It is. The conclusion, as the researcher stated, was inescapable. If the Jeans hypothesis were correct, the total number of planetary systems formed in the entire galaxy over 10 billion years would be about 10.
10.
You could count the number of star systems with planets in the entire Milky Way quite literally on the fingers.
And that catastrophically rare outcome just flew in the face of what was becoming the accepted view, that the universe is probably not so stingy, that we're probably not that exceptional. If that's true, this theory has to be wrong.
But rarity wasn't even its only problem. The Jeans hypothesis also suffered from the exact same underlying physical flaw as Kant-Laplace.
The momentum problem again.
Just wouldn't die.
Failure number 2. Momentum and condensation. But didn't the close passage of the other star fix that?
Not sufficiently, no. More detailed mathematical calculations done by researchers like Henry Norris Russell and N. Parisky showed that even if you could successfully pull the filament off the sun, the resulting planets would inevitably have orbits that were extremely small. They'd be confined way too close to the sun. The passing star simply couldn't impart enough rotational velocity combined with enough distance to account for the massive orbits and that 98% of momentum held by Jupiter and Saturn.
So even a stellar drive-by just wasn't fast enough or wide enough to create the system we actually live in. That massive angular momentum of the outer planets remained unsolved.
And then came the final, devastating physical blow. Astrophysical calculations, most famously by Lyman Spitzer, showed that this superheated gas filament, violently ejected from the sun's surface, would likely not condense into planets at all.
Why not? Just too hot.
Way too hot and way too low in density. The high kinetic energy from the tidal forces, combined with the extreme heat of solar material, meant that the gas molecules would just be moving too fast. They would simply dissipate into the surrounding space. It wouldn't cool and clump, it would just fly away into the void.
So by the late 1930s, you have these two giants of cosmology. One theory proposing an orderly internal evolution, the other a catastrophic accident, and both were fundamentally broken by the exact same physical requirement.
The enormous angular momentum of the outer planets and the inability of either mechanism to create those distant, high-momentum orbits.
And that failure forced researchers to start thinking outside the box, which led to what we're calling the modern revival. Theories that managed to import the necessary angular momentum from external sources, but without relying on incredibly rare star collisions.
Exactly. Which brings us to the modern revival. Capture hypotheses, Wolfson and Schmidt. And what's so fascinating is that the idea of an external event, a catastrophe, actually returned, but with a massive upgrade in the physics.
Yes, the 20th century challenge was clear. You had to find a way to import high angular momentum from outside the sun that was either more probable than 1 in a quadrillion, or that inherently linked planet formation to star formation.
And that led to two very different, very clever approaches.
Let's start with the updated tidal model, the Jeans-Wolfson modification. How did Michael Wolfson modify the catastrophe theory to try and solve the momentum and the dissipation problems at the same time?
Wolfson had a brilliant insight. He realized that the object causing the tidal force couldn't be a typical, dense, mature star like our sun. That's what caused all the problems, the low momentum orbits and the hot gas dissipation issue. He proposed that instead, the gas stream was ejected from a passing protostar.
Okay, what exactly is a protostar in this context? What makes it different?
It's a pre-stellar object. It's still forming. It's essentially a loose, vast cloud of gas and dust that hasn't fully contracted and ignited to become a true star. And critically, Wolfson posited it was an object of enormous physical size but a comparatively small mass.
Give us the dimensions on that.
The size was estimated to be about 10 times the radius of Earth's current orbit. Huge. But its mass was only about a quarter of our sun's mass. So you have this big, fluffy object that spans an immense volume of space, but it lacks the density and the high relative speed of a mature star.
Wait, how does being big and fluffy help? Why does a loose protostar solve the problem that a dense star created?
It solves both major flaws at once. First, the sheer physical volume of the protostar means the interaction happens over a much, much larger radius. This allows the captured material to achieve highly eccentric orbits that are incredibly distant from the sun. He calculated up to 30 astronomical units, which is out past Neptune's orbit. That immediately fixes the momentum problem.
Because the captured material is already starting out with the necessary distance, which gives it that high angular momentum right from the start.
Exactly. And second, because the protostar is loose and diffuse, the material being ejected isn't superheated, dense plasma being violently ripped from a star's surface. It's more like loosely bound gas clumps being gently captured from a vast, low-density cloud. And this completely avoids Spitzer's dissipation problem.
That is a really clever modification. The protostar transfers momentum efficiently because of its huge size, and it avoids the thermal dissipation problem because of its low density.
Right. And the sources describe the captured gas clumps ending up on these highly eccentric, almost hyperbolic orbits at first.
So how do they become the nearly circular orbits we see today?
That requires a secondary mechanism. The idea is that the captured material wouldn't have been moving through empty space. It would have been surrounded by a kind of residual atmosphere of uncondensed gas and dust, a vast swirling medium that would have provided drag.
Friction, basically.
A kind of cosmic friction, yes. This gaseous medium would slow the clumps down, causing their wild, eccentric orbits to quickly circularize. The calculations suggested this process might only take a few million years, which is very fast on a cosmic scale, fast enough for each slowed down clump to then evolve into a protoplanet. The model even manages to handle the formation of large planets and their satellites, which could separate due to asymmetric compression as the protoplanets themselves contracted.
That sounds incredibly comprehensive, at least for the gas giants. But the original critique of Wolfson still seems to apply. This whole thing still relies on an accidental closed passage. It's still a catastrophic model.
And that, according to the sources, remains the sole vulnerable point of this modification. While protostars are far more common in stellar nurseries than mature stars are out in the galactic field, the calculations still show that this mechanism would only result in about one planetary system per 100,000 stars.
Okay, 1 in 100,000 is infinitely more probable than 1 in tens of billions. I'll give it that. But it's still extremely rare, especially if we look around and find that, 80% of stars seem to have planets.
And the sources make the future verification crystal clear. If we look out and confirm with certainty that exoplanetary systems are common, that they are a standard byproduct of star formation, then the Wolfson hypothesis, which predicts scarcity, will be finally buried.
So the fate of the modern tidal model really rests on just how often we find planets out there. But there was another major modern model that avoids the rarity problem entirely because it ties planet formation right back to star formation itself.
Yes. Let's talk about the Schmidt-Littleton accretion hypothesis.
Okay.
Its model originated with the brilliant Soviet scientist Ott Yulievich Schmidt back in 1944, and it was later refined by Littleton in 1961. And the core mechanism is just this beautiful conceptual flip. The sun, already in its modern form, was not the victim of a tidal force, but the collector. It passed through and captured material from a vast existing gas-dust nebula.
So the sun acted like a cosmic vacuum cleaner, just moving through a dense cloud of debris and sucking it up.
Precisely. And this simple idea inherently solves the angular momentum problem effortlessly. The whole 98% puzzle just vanishes immediately.
Why? How does that work?
Because the captured cloud material is large, diffuse, and most importantly, external to the sun. It can possess an arbitrarily large initial angular moment relative to the sun. The rotational energy was never stripped from the sun in the first place. It was injected into the system from the outside.
That is a stunningly simple piece of intellectual problem solving. It just bypasses the central issue that killed 2 centuries of prior thought. But for the sun to successfully capture a substantial amount of material from a nebula, there must be a pretty tight physical constraint on that interaction, right? I mean, if the sun moves too fast, the material would just fly right past it.
There is a severe constraint, and this is the most profound implication of this entire theory. For the sun to capture enough mass from the cloud to actually form a planetary system, its relative speed to the nebula has to be incredibly low, on the order of only 100 meters per second.
100 meters per second. That is glacially slow on a cosmic scale. I mean, the internal movements within the cloud itself must be at least that fast, so for the relative speed to be that low.
The implication is profound, exactly. It means the sun was not simply a tourist passing through some random cloud of opportunity. To satisfy that low relative velocity requirement, the sun must have been deeply, intimately involved with that cloud. It was likely stuck in the cloud and shared a common origin with it.
And this is where we see the full circle of intellectual history. By trying to solve the angular momentum crisis with external capture, the physics actually forced cosmologists right back to the original philosophical concept of Kant.
Yes, that planetary formation is closely linked to the process of star formation itself, all occurring within a common birth environment.
Wow. The Schmidt accretion hypothesis basically requires the formation of planets to be a natural, expected, and common corollary of star birth inside a stellar cloud or association. It's not an ultra-rare catastrophic event.
It brings the order back, but it grounds it in the, let's call it the violence of momentum capture, not the gentleness of contraction.
This has been a fascinating journey through scientific failure and an eventual conceptual synthesis. We started with this beautiful, orderly philosophy Kant-Laplace, and it was immediately derailed by math and physics.
Well, that's the story of how knowledge progresses, isn't it? The key takeaway has to be that dramatic shift in thinking, forced entirely by the angular momentum paradox. We move from orderly internal evolution, which failed on momentum transfer,
To a catastrophic accident with genes, which failed on probability and still couldn't quite fix the momentum problem.
and then finally to the modern capture and accretion models.
And the modern models, both Wolfson's and Schmidt's, succeeded specifically because they allowed the system to acquire that massive angular momentum from a large, external low-mass object or a gas cloud. They effectively solved the 98% paradox by just importing the spin from outside.
And both those concepts ultimately pivot the origin of planets towards the broader, more common processes of star formation. Wolfson's model requires the prevalence of protostars in stellar associations, where you have massive stars forming first and leaving behind these necessary loose objects for later encounters.
And Schmidt's model demands that the sun be almost a co-parent with the nebula, which implies that planetary birth is just part of a star's standard natal environment. It has to be, to satisfy that constraint of 100 meters per second.
This is why the unifying trend is so powerful. The prevailing theories are all moving away from the accident narrative and back toward the concept of planetary systems being a standard byproduct of stellar birth, which is exactly what the emerging empirical data from exoplanet observations seems to be suggesting.
But, as we mentioned, the modified catastrophic model Wolfson's theory, it still retains that one crucial vulnerability.
And that really is the central point of verification for the immediate future of this research. The fate of the modern, low-probability catastrophic hypotheses hinges entirely on the confirmed frequency of planetary systems around nearby stars.
If we confirm that exoplanets are abundant, that they're common, that virtually every star has them, then Wolfson's hypothesis, which predicts only one system per 100,000 stars, it just becomes obsolete.
If planetary systems are common, the catastrophic models based on rarity are buried once and for all.
So the search for our own origins has gone from philosophical speculation to complex astrophysics, and now it really rests on empirical data being gathered by modern telescopes. We've moved beyond asking how the momentum was distributed to where it came from, and now finally to just how often it happens.
It's just incredible to think that the single greatest challenge to understanding our cosmic home, that simple fact that the planets orbit so much faster than the sun spins, forced us to completely abandon the idea of a simple, serene, orderly genesis.
It seems it taught us that cosmic stability might actually require a massive input of external energy and in some ways a kind of initial violence to strip the core of its spin.
It's a much more dynamic picture.
And that leads us to our final thought for you, the listener, as you reflect on this deep dive. We have established that the planets hold 98% of the solar system's total angular momentum. All of the systems spin.
So I want you to think about what this massive concentration of orbital energy, not stored in the powerful, massive central body, but in the distant and tiny moving parts. What does that tell us about the fundamental dynamic forces required to build a stable system like ours?
Why wasn't the sun allowed to hold on to its own spin? What cosmic mechanism, operating at the very beginning of time, was powerful enough and persistent enough to not only strip the sun of its rotational energy, but to distribute that colossal energy almost perfectly to the outer regions of the system?
It really suggests that our system's stable circular order was born not from some serene collapse, but from unexpected forces, like a vast, diffuse protostar passing by, or a slow, careful capture through a shared birthplace, that were just highly efficient at transferring momentum to the periphery. It made the sun relatively slow so that the planets could be fast. And that's something worth pondering the next time you look up at Jupiter in the night sky.
An excellent thought to end on. That wraps up our deep dive into the Battle of the Giants and the surprising and still unfolding story of the origin of the solar system.